In this lesson, we're going to review some graphing methods and also discuss some new methods to graph called transformations. So the first example, we have a linear function and it asks us to graph the function f of x equals 2x minus 7. So remember, whenever we're graphing linear equations or functions, we want it in the form of y equals mx plus b. These functions are already going to be in that form, but when we're dealing with equations, we want to solve for y so that y is isolated. Now to review, the coefficient of the x is our slope, and our constant at the end is our y-intercept, which will be our starting point when we graph. The y-intercept is the point on the graph where the line passes through or touches the y-axis. So in this case, we have f of x equals 2x minus 7. So our slope is 2, and we're going to write it as a fraction because remember, slope is rise over run. And our y-intercept and our starting point is the point 0, negative 7. So on our graph, we begin at our y-intercept, which is negative 7. And the change from point to point, or our slope, is positive 2 over 1. So the change in the rise is positive 2, so we move up 2 units. And the change in the run is positive 1, so we move to the right 1. And we simply connect these 2 points with a straight line. Our next example is also a linear function. H of x equals negative 3/2 x plus 4. So again, we want to identify our slope, which in this case is negative 3 over positive 2. Notice the negative goes with one or the other and not both. And our y-intercept, which is going to be our starting point, is positive 4. So in our y-axis, our y-intercept, we plot our first point, which is positive 4. And our slope has a change in the rise of negative 3 and the change in the run of positive 2. So from our starting point, we go down 3 units since the numerator is negative, and to the right 2 since our denominator is positive. And again, we just connect these 2 points with a straight line. Our next example says graph the parabola. How do we know it's a parabola? Because it's a quadratic. That means x is raised to the second power. Graph the parabola by plotting 5 points, the vertex, 2 points to the left, and 2 points to the right. So let's go ahead and find the vertex. So the vertex, since it's in what we call the standard form, is pretty much whatever makes this 0, which is positive 2, and then this value at the end being added or subtracted, in this case, negative 3. So we have a vertex at 2, negative 3. And now we need to find points to the left and points to the right. So in our graph, since our vertex is 2, what we want to do is use the x value of the vertex 2, which we already know the y value is negative 3. And we're going to choose 2 points to the right, 3 and 4. So we come back to our original equation, and we're going to substitute first 3 in for x, so that'd be 3 minus 2 squared minus 3, which is 1 squared minus 3, and 1 squared is 1, minus 3 is negative 2. Next, we're going to substitute 4 in for x. So y equals 4 minus 2 squared minus 3. 4 minus 2 is 2, so we have 2 squared minus 3, and we know 2 squared are 4, and 4 minus 3 is 1. So we're going to come down to our graph. So again, we know we have 2, negative 3, we have 3, negative 2, and 4, 1 for 2 points to the right. So let's go ahead and plot those. So 2, negative 3, we move to the right 2 and down 3. Then we have 3, negative 2, to the right 3 and down 2. And we have 4, 1. So although we'll talk about this a little later, there's really no calculations we need to do to find values to the left. A parabola is symmetrical through the vertex. So there's an imaginary line called the axis of symmetry that's going to divide our graph into 2 identical parts. So the equation of our axis of symmetry is always x equals whatever the x value of our vertex is. In this case is 2. So it's a horizontal line that goes through our vertex. What it does is divides our graph into 2 identical parts. So when we move up from our vertex to our first point, since there's a point 1 unit to the right of our axis of symmetry, there's a corresponding point 1 unit to the left. So now we move up to our next point, and since there's a point 2 units to the right, there's a corresponding point 2 units to the left, always. So there we have our parabola. And notice we only had to do calculations for one side or the other, because then we can use our axis of symmetry to plot the other 2 points. Next, we're going to start talking about transformations. So transformations make it easy to graph different functions. So when we talk about parent functions, we're talking about what the original functions are before we add or subtract or do any type of transformation. So for instance, we just talked about a quadratic function. So an x squared function, and we'll go more into depth into this in a minute, but we know that the shape is a parabola. So our parent function is the x squared function. We're also going to deal with absolute value. So our parent function is the absolute value, and our graph is going to be a V-shaped function. We're also going to discuss the square root of x. And our graph's going to look something like this. We're going to talk about an x cubed function. And our graph's kind of going to look like an S. So those are 4 examples of parent functions. Now, what transformations are the shifting of our parent function from their original points. So we're going to talk about horizontal shifting, vertical shifting. We're going to talk about reflections on the x-axis and on the y-axis and how to identify it. So let's look at the parent functions, the x squared. So notice inside parentheses, if I'm adding a value to x or subtracting a value from x, and notice the parent function, it's squared. And notice that the value being added or subtracted is within the parentheses. This would be a horizontal shift. So in the first example, our whole graph, our parent function, is going to shift 2 units to the left. When it's positive, it's going to be shifting to the left. And when it's negative, it's going to shift horizontally, in this case, 3 units to the right. Let's look at another parent function, the absolute value. So notice, what's being added or subtracted is within the absolute value. So in the first case, we're going to shift 1 unit to the left. In the second example, we're going to shift 2 units to the right. And again, one last example dealing with square root. And again, notice that the value is underneath the radical sign. So in the first example, since it's addition, we're going to shift to the left 3 units. And since it's underneath the radical sign, we're going to shift 4 units to the right. So again, when it's positive, we're shifting to the left. And when it's negative or subtraction, we're shifting to the right. And again, notice the location of the values within the parentheses, within the absolute value, included underneath the radical sign. So let's look how that differs from a vertical shift. So notice in our first example, the 1 isn't in parentheses and not being squared. Same with the -3. So in these cases, these are vertical shifts, so it would shift our graph up or down. So in the first example, our graph would shift up 1 unit since it's plus. In the second example, our graph would shift down 3 units since it's subtraction. Again, absolute value. Notice the 2 is not within the absolute value sign. Neither is the -4. So these would represent vertical shifts. So in the first, it would shift up 2 units. And in the second, down 4 units. For radicals, same thing. So here we'd have the square root of x plus 5, the square root of x minus 7. Notice again, the 5 and the 7 are not underneath the radical sign. So the first would be shifting up by 5 units, and the second would be shifting down by 7 units. And we'll talk about this, and you'll see how this works when we graph. Now let's talk about reflections. Reflections, more or less, are flipping the graph across the x-axis, or for reflections on the y-axis, it flips the graph across the y-axis, and I'll show you an example. So an example of this would be if we had our parent function being x squared, for instance. We know the shape of the graph is a U-shaped graph. When there's a minus sign in front of our function, even if there's a number with it, but in this case, I'm just keeping it as just the minus sign in front of x squared, it reflects on the x-axis. So what it does is flips our graph. So now it's pointing downward. So now let's look at a reflection on the y-axis. So we'll use the square root function. So the square root of x function is a graph that looks like this. Now notice the negative is underneath the radical sign. So we're taking the opposite of whatever x is. So what that does is reflects our graph on the y-axis. So now our graph would flip over and be facing the other direction. So now let's look at graphing functions, and we can graph them with reflections. So what I'm going to do first is graph the parent function. So in this case, our parent function, and I'm going to name it g of x, is the square root of x. I'm using a radical sign in this problem, so we know our parent function is the square root of x. If you want to find exact values, we can make a table of values. So if x is 0, the square root of 0 is 0. If x were 1, the square root of 1 is 1. If x were 4, the square root of 4 is 2. And notice I'm only using perfect squares for the x column. So if I wanted another one, I would use 9, and the square root of 9 is 3. So we could plot these points: 0, 0, 1, 1, 4, 2, and 9, 3. So I'm going to use a broken line so you can see what our parent function would look like. So now what is happening with our parent function? So notice this -3 is not underneath the radical sign. Therefore, that's a vertical shift. So our whole graph is going to shift down by 3 units. So that means every point on this graph is going to change by 3 units. So that's going to just affect our y values. So instead of this being at 0, 0, if I'm going down 3 units, it should be at 0, -3. My second point, that point at 1, 1 here, that's also going to shift down 3 units. So you can count down 1, 2, 3 units and put the next point. And 4, 2 also is going to shift down by 3 units. And also where we had 9, 3, that's also going to shift down 3 units. And now we have our new graph. Notice we didn't have to do any calculations. So when we're dealing with transformations, it's going to make changes to our x or y values and simply shift our graph up, down, left, right, or a combination of. And we'll look at some more in a second. So here's an example. Below is the graph of y equals x squared. Translate it to make the graph of y equals the quantity x minus 4 squared minus 3. So we knew it was a parabola because of the square, this being squared. Now we have to deal with the transformation or shifting. So when we look at our graph, the x minus 4 squared. Since we have a -4 inside the parentheses, remember that's a horizontal shift, and since it's minus, it's going to be to the right. So our graph's going to shift 4 units to the right. Notice at the end, we have the -3, which is outside the parentheses. So that means our graph is going to shift 3 units down. So we take our graph, our 0, 0, and that's going to shift 4 units to the right and 3 units down. So our new vertex is at 4, -3. So remember, every point shifts by that amount. So we can take this point 1, 1 here, and that also shifts 4 units to the right and 3 units down. And this point right here, 2, 4. So that's also going to shift 4 units to the right and 3 units down. So keep in mind, we don't have to do this a lot because remember the concept of the axis of symmetry. Remember the axis of symmetry, that imaginary line that divides the graph into two identical parts. So if we have a point 1 unit to the right, we'd have a similar point 1 unit to the left. So we keep moving up that axis of symmetry until we come to the next point, which is 2 units to the right. So we'd have a point 2 units to the left as well. And this would be our new graph. So again, transformations, we don't have to do any calculations whatsoever. We're just literally shifting the graph. So this next example, we have graph the parabola y equals the quantity x plus 4 squared plus 2. So again, we know by looking at this x plus 4, since it's in parentheses, that's going to be a horizontal shift, 4 units to the left. Why left? Because it's plus. And since we have a plus 2 at the end, we're going to shift our graph 2 units up. So our vertical shift would be 2 units up. So 4 units left, 2 units up. Now from what? It's a good idea to become familiar with your parent functions. So a parabola, we know, starts at 0, 0. So this is the parent function, 1, 1. How do I know it's 1, 1? Because if our parent function is x squared, whatever x value we choose, we square it to get the corresponding y value. So the next unit being 2 for x, if I square it, I get 4. So again, what am I going to do? I'm going to use my axis of symmetry until you get used to this to plot my other values. So I'll have 1 unit to the left and then 2 units to the left. And there's my parent function. What do I do with my parent function? So remember, we're shifting it 4 units to the left and then 2 units up. So I shift my vertex 4 units to the left at -4 and then 2 units up at 2. So then I'm going to do the same shifting for the other values as well. So again, I'm going to shift every point 4 units to the left and 2 units up. And then you can use, again, your axis of symmetry to plot your other points. And then there's your new graph after the translation. Okay? So let's deal with absolute value. So here we have the parent function, the absolute value of x, and its graph for us. And now we need to make the translation. So again, pay attention to what's inside the absolute value symbol. So since it's a +2, we know we're going to shift, the horizontal shift is 2 units to the left. Because it's plus, it's to the left. And -3, our vertical shift, is 3 units down. So I'm going to take my absolute value graph and shift it 2 units to the left. So it'd go to -2 and then 3 units down. And again, I'll do that for each value as well. So you can take maybe the point 1, 1 here. And then again, that's going to shift to the left 2 units. And then count 3 units down for this. And just like we have with our parabola, we'd have the same thing, a line that goes through the vertex that divides our graph into 2 identical parts. And then we would simply connect the points. So the next example, we're dealing with the square root graph. Our parent function is the square root of x. we're asked to translate the square root of x minus 2 minus 3. So again, we pay attention. What's underneath the radical sign? The minus 2. So that represents a horizontal shift. Remember, if it's a minus, we're going to the right 2 units. And since it's a minus 3, our vertical shift is down 3 units. So we come to our starting point, that's 0, 0. We go to the right 2 units, so it would be at 2. And then we go down 3 units from there. And so again, we can take this point, maybe 1, 1, or you could go to 4, 2. It doesn't make a difference. You go to both. And so we're going to go to the right 2 units first and down 3. And then we'll do the same thing for 4, 2. We're going to go to the right 2 and down 3 as well. So again, we'll connect these. So again, you'll find a couple points on the graph. And how did I know it's 1, 1 and 4, 2? Because you could plug it into the square root of x. The square root of 1 is 1. The square root of 4 is 2. So that's where these numbers are coming from. And then again, all you do is you do your shifting based on those points. So next, we have the graph of a cubic function. That means x to the 3rd power. We're going to transform it when we're given 3 times the quantity x plus 1 cubed plus 4. So what's going to happen in this graph? We have only one thing that's a little bit different. So since the x plus 1 is inside parentheses being cubed, that's our horizontal shift. And since it's plus, we go to the left, not right. We go to the left 1 unit. Since we have a plus 4 at the end, that's a vertical shift up by 4 units. And we have what's called a vertical stretch. When there's a number in front of our function, that stretches our function. So we have a vertical stretch of a multiple of 3. So that kind of works the same as the slope. So what we're going to do is we're going to take our point 0, 0. We're going to move to the left 3. Excuse me, to the left 1 and up 4. Now to find our next point, what we can do is the same thing as slope. From this point, we can move up 3 and over 1. And we can also move down 3 and over 1. So we're going to have that S-shaped graph. After our translation. Now what they're going to do is give you 2 graphs. They're going to give you the parent function, and they're going to do a translation and ask you what the function would be after the translation. So we know that, again, the original function it's given, f of x equals the absolute value of x. That's why we have that V-shaped graph. That's the blue one. How do we get to the red? So what we're going to do is pay attention to those points where the f is and where the h is. How do we get from f to h? So we had to move to the left. So keep in mind, we have the absolute value as our parent function, and we have x. Now, if there's a shift horizontally, left or right, we need to add or subtract something to this within the absolute value symbol. So since we move to the left 4 units, remember if we move left, that's plus, and the number of units we move is 4. So that's moving our original parent function to the left 4 units. Now it's not on our x-axis. The graph moved up. So remember, if we're moving up in a vertical translation, that's plus. And it's just how many units we moved up, and in this case, 2. So since our graph moved 4 units to the left, we have x plus 4 in the absolute value symbols. And since it moved up 2, we have plus 2. Now we're going to talk about piecewise functions. So here we're given h of x equals -3 if x does not equal 0. And h of x equals -2 if x equals 0. So what I do is I set up table of values. So I do it if x does not equal 0 and if x equals 0. So I make an XY table for both. So it says if x does not equal 0, I still use that to begin with, that 0. So I use 0, and since it can't equal 0, I'm going to write the word open next to it, meaning I need to put an open circle at that point. So if x does not equal 0, the answer is -3. So again, I'm just putting that as my starting point, remembering that that point is not included. Now I'm going to choose values to the right or left. So I'm going to choose 1. So since 1 does not equal 0, my answer would be -3. 2 doesn't equal 0, so my answer would be -3. Then I'm going to go on the other side of 0 to my negatives. So if x were -1, y is still -3, and -2, -3 as well. So again, remember, in these tables, I always use that point as my starting point. It's solid if it's included, and it's open if it's not. So in this case, I use 0. So if x equals 0, my answer is -2. I don't need to do any other points because that's all it is. If x is 0, y is -2. So what I'm going to do is plot. So I'm going to start with 0, -3. So 0, -3 would be here. So I'm going to use an open circle. Then I go to 1, -3, which is here. 2, -3. And of course, it would continue on forever in that direction. Also, if x is -1, y is -3. And again, -2, -3, and it would continue on indefinitely in that direction. So I've taken care of the graph of my first table. Now it says if x is 0, y is -2 is included. So that's all I need to do is put a single point there. So my last example, I have supposed that the function f is defined. And again, I have a piecewise function because I have here 2 expressions or 2 equations dealing with 2 exceptions or rules here. So I need to make a table of value for both. So I'm going to do one for x is less than 1 and for one if x is greater than or equal to 1. So remember what I said. Even though the point isn't included, I always include or begin with that value. So I wrote open because x cannot equal -1. It's the values less than -1. So it says if x is less than 1, I use 2x minus 1. So if I use 2x minus 1, I substitute the 1 in there. And y would be 1. Then I choose another value less than 1, 0, and I'm going to do -1 as well. So again, I plug it into the 2x minus 1 because I follow this if this exception is in effect. So I plug -1 in. So 2 times -1 minus 1 is -2 minus 1, which is -3. And I'm going to do the same thing for 0. 2 times 0 minus 1, 0 minus 1 is a -1. So I'm done with my first table. So again, remember, I use the value given, and the values that are greater than 1 could be like 2 and 3. When that's the case, I use the second equation or function. So I use the opposite of x plus 2. So I plug 1 in to begin with. So that's -1 plus 2 is 1. Next, I plug 2 in. So -2 plus 2 is 0. Then I plug 3 in. -3 plus 2 is -1. So what I'm going to do is graph these on the same coordinate plane. So again, I'll rewrite this. So for the first one, I'm going to be 1, 1, with that being open. 0, -1. I'm taking this just right off my graph or my table. And for the second one, I'm going to be graphing 1, 1, and that's included. And then 2, 0, and then 3, -1. I'm taking these directly from my tables. So for the first one, I come to 1, 1. And remember, it's an open circle. I go to 0, -1. And then -1, -3. So this would continue on forever. Next, I come to the second one, which is 1, 1, and it's included. So this part that was open now will become closed because it's included in the second one. Then I go to 2, 0, and then 3, -1. And again, my graph would continue on forever.